Today we have the Viture Pro XR Glasses. Again, same type of birdbath optic design for these particular glasses that we've seen in the X Reals and the Ray Neos, with one key differentiation for this particular price point, which is that we have electrochromic dimming on the glasses themselves. So we'll see what that means, but this is a very, very good feature to increase the contrast of the display as we actually are able to dim the outside light. And this is typically done in the more budget models with a fixed level of dimming already molded into the lens element. One other unique feature of these Viture Pros is that we have myopia adjustment. We have actual dials that allow you to tune in the focal length of the display to your eye, such that you actually don't need prescription lens inserts for this particular device within a certain range. So this is actually a really great user experience for those who will need myopia adjustment in their headset. But overall, I would say these glasses, after having used them for a couple of days now, are great. They do not have the same standard Type-C USB connection that we've seen in some of the other glasses. They have their own magnetic pogo pin attachment that we see in just the Viture Pros. It's quite nice, but unfortunately, many people report hair getting stuck in this connection, which can be quite frustrating, I'm assuming, for the user. The Viture Pros are same 1920 by 1080p display that we've seen from a lot of other headsets. In the future, we know Viture is going to go to 1200p for some of their Luma line glasses, and ultimately 1440p as we get more and more high-density micro OLED displays. But for now, we're looking at a 1080p display, likely a Sony panel that we'll take a look at when we break this open. It's rated at 4,000 nits. This, I think, is a little bit misleading because it does not tell you the total brightness that is delivered to your eye. It tells you the brightness of the panel itself. And so unfortunately, you are not going to get 4,000 nits delivered straight to the eye. More closely, I think you'll get around 600 or 700, similar to the X Real Airs that we broke down earlier. But that's okay. I think this is, again, plenty bright enough for indoor applications. And more importantly, with the electrochromic dimming module, and we'll take a look at that in depth when we break this down. We can actually see me turn off the electrochromic dimming module here. This gives us sufficient brightness with the dimming module on, such that we actually have a much better contrast than we've actually seen in some of these other static glasses, which tend to have maybe just a fixed lens darkness that you cannot control. And most importantly, you can turn the display off here and see through to the world a lot better than you can in some of the other glasses that we have. When the displays are off, you're just going to have very, very dark sunglasses, almost unusable indoors. So this is quite a great user experience, again, for the similar price point that we're seeing for the Airs. Both Ray Neo and X Real and some of the other emerging brands definitely have this electrochromic dimming module embedded into their future products, but at a much higher price point. The overall optical experience, we won't talk about it too much because we've extensively talked about these simple birdbath optics designs. But overall, it's a great experience, 120 hertz, like all the other panels that we've had available to us. No choice of lowering the refresh rate like we've seen in the Ray Neo, which means that we're going to have a very high or elevated battery draw from this device, compared to a device like Ray Neo's, where you can adjust the refresh rate lower to ultimately save on battery life. Again, this is simple pass-through screen, so we don't have any native 3 degree of freedom tracking to the headset. This is done via a separate app. It's called the Spacewalker app for Viture. This is fine. I don't think we're seeing any novelty in how this is implemented. But for a sub $300 pair of glasses, I think the Viture Pros are actually quite good. And again, the optical system that includes both the novelty of electrochromic dimming, coupled with the fact that you have myopia adjustment built into the optical mechanism, really gives this a much wider, broad applicability for most people who are trying to dip their toes into the XR glasses space. So from a pure user experience perspective, I think Viture has done a fantastic job of giving us an introduction to what this could look like in the future. So we'll now take these apart and take a look inside to see what the actual mechanism looks like for the myopia adjustment, and then break apart the optical module into the display and lens modules and see if there's any unique films or optical surfaces that Viture has built into their device. So here we have the glasses. You can see here the birdbath optical element that we've got to project the actual display to the user's eyes. We can see that by using the little turn dial, we're actually moving the lens plus display assembly in the optical module. This allows us very easily to change the focal length of the display projected onto the user's eye and avoid having to have a prescription lens in between the birdbath optic and your eye to correct for myopic vision. Entry into this device is relatively simple. We have 4 hexalobe screws on 2 on each stem, where we actually have the stems collapse into their folded position. So we'll remove these, and we'll also remove the nose piece, where we have further hexalobe screw available for us to take out. Okay, so now that we're able to pull this back part off, and remove it gently to make sure that we don't do any damage to the flex cables, and remove the 2 front spudgers as well. So one thing you'll see is the electrochromic module that we have here behind the birdbath optical module. This, if you push into it, we actually see a bit of distortion. You get some darkening where you're pressing. And if you're familiar with LCD, liquid crystal displays, it's essentially what we have here is one large LCD pixel, where in the off state with no power, the liquid crystal module allows up to 40% of the light from behind it to pass through the element. But then as soon as we power it on, for example, by plugging in the device, you'll see that now the element goes dark. And this is essentially what gives us a really nice contrast to the entire screen as we use these glasses with the electrochromic dimming on. And again, if we turn it off by just pushing the button, again, we can turn it on and off from the button on the left stem of the glasses. Now that we have the device powered on with the optical module exposed, we can take a look inside. This is essentially what you're able to see through the eyepiece when you're actually wearing these devices. And so the overall quality of the display is quite good. It's very similar to all of the other competition that we have. But again, one of the really impressive aspects of this is the ability to have diopter control. This dial that we see here that's user serviceable, to allow you to change the focal distance of the display relative to your eye and prevent the need for introducing prescription lenses in front of the optical module. So we can see what this might look like if we take a look here. As I turn the dial, you'll notice that the image gets further and further out of focus, but luckily the camera on this phone is quite smart and it automatically adjusts the focus. What you'll actually see is that the screen is just getting slightly smaller or slightly larger, because again, we're bringing the screen closer or further away from the main reflective elements in our optical module and just shifting it in this direction with the dials on either side. So quite a clever design by Viture, and really looking forward to being able to open that up and see on the inside. Overall, quite a nice design on the inside. We actually have a metal bracket that the optical module is sitting flush against, which allows quite a bit of thermal dissipation, a lot of heat that's generated by the display to be sucked out and dissipated throughout the entirety of the optical assembly. Something that XReal also does with its magnesium alloy frame, but unfortunately Ray Neo does not, with a more plastic construction on the inside. So we'll continue to tear this down and expose the optical module more completely. One thing we'll want to do next is move the stems out of the way. So we'll turn off power to the device by unplugging it. And if we move the stem out of the way, we can see that we have one Phillips head screw right here with a matching one on the left side of the frame, as well as two in the center that we're going to have to remove before we can take off the module. Once we've removed the 4 screws on either side of the temple and by the nose bridge, you can now see that the optical module uses 2 flex connectors for the electrochromic dimming modules in the front, and those flex connectors are going directly into this central motherboard. So we'll have to unplug these before we go any farther, lest we damage those and never be able to use the dimming module again. These are just little flip tabs that we can use on either side, covered by a small bit of Kapton tape. But once the flip tabs are flipped up in the upright position, we can remove the electrochromic dimming module. And this essentially is a liquid crystal cell, just one cell for either side, that we're going to be able to hopefully turn on a little bit later. One thing to note, unlike Ray Neo and more similar to the XReals, this uses 2 separate optical modules. So we don't have a single body that houses all the mechanical tolerances for our displays and their distance to each of the individual lenses the user will see through. There is a single left optical module with the optical module housing dedicated to that module here, and a right optical module housing on the right side of the screen. Essentially, this means that Viture has to have 2 separate sets of tooling, both for left and right. Again, increasing manufacturing complexity a bit, but ultimately giving us more control over both the left and the right side modules, should there be slight differences in the manufacturing process and the manufacturing output. So again, we can expect a slightly higher quality display because of it, delivered to your eye. Okay, so after we remove the Phillips head screws that connect the optical module here and here to the stainless steel chassis, as well as take off the gear mechanism that allows us to change the focal distance between the lens panel assembly to the eye of the user, we'll just need to pop off the connector that you see here. And that allows us to pull off the optical module from the main frame of the birdbath optics. The Diopter adjustment mechanism is held in place with 3 Phillips head screws. Once we remove all of these, we're going to be able to just pop off this mechanism from the main plastic housing of the optical module. And you can see here that essentially what we left, we've got the lens assembly, lens module. We'll put that to the side for now. We're left with the lens and the display panel on the element that actually allows us to change the focal depth of the lens. So this flat plate that the panel sits on essentially articulates on a linear screw that's on the far left of the screen right now. We can add this gear back in. And then if we just turn the gear clockwise or anti-clockwise, we can see how the plate moves up or down on that articulated screw, allowing us to change the location of the focal point from the image through the birdbath optics. So really, really nice design here by Viture. Now we've unplugged the display panel from the ZIF connector that's located on the back side of the adapter adjustment mechanism. And we can take a look at more detail of how the field lens is made to the display. So we can wedge something in between the field lens here. And one nice thing is that Viture hasn't actually glued this down along the entire display panel like most manufacturers do. It's only glued in one location here at the top of the screen. But it allows us to very cleanly remove this lens and see the optical film that's left. We've done a little bit of damage to this optical film. We can see a crack in the polarizing films here. But overall, this is much, much easier to access and service and potentially even replace in future designs than any of the Viture competitors today. So one thing we want to check here when we have the display panel mostly removed from the backplate is, do we still get power to the display? And so if we plug in the main logic board again, we can see that we do get an image on the display, but unfortunately we are not getting the actual image that's being mirrored from the host computer. We're just getting white screen. And so I suspect that we've done some damage to the trace circuitry, that it fans out from the microdisplay to this flex cable during our attempt to wedge this off of the backplate. Again, Viture seems to use a very strong glue here, and unfortunately during disassembly we'll not always be able to keep the very fragile silicon. Taking a look at the display module, we can see here that it's a 4-component module. One, the left side, we have the heatsink. This is the component that actually allows for the myopia adjustment by virtue of the linear screw that this is threaded through. And on top of this surface, we also see the thermal pad as well as the very strong glue line that we have between the display panel and the backing. This ultimately is what caused damage during this teardown and prevents us from lighting up the panel in this state. Nevertheless, the display panel is a Sony ECX348E panel, a 0.55 inch 1920 by 1080p display. Again, quite a standard display from Sony, though a little bit smaller than the competitors are typically using in this form factor. Nevertheless, it does provide a very large image delivered to the eye. So I suspect the difference between 0.55 or 0.6 inches to the user is not that large, maybe a slightly reduced field of view. The optical film is actually quite interesting here because it is not a traditional quarter wave plate plus linear polarizer combination. We can take a look at this film with another linear polarizing element put on top of it. What I'm doing now is I'm putting a linear polarizer with an axis that's 90 degrees relative to the absorption axis of that polarizer. And what we see is that we have a complete block in the light transmission through these two optical films. We turn the top film to be parallel with the absorption axis. We now have transmission through both films. What this is telling us is that we don't have a quarter wave plate on this film. Typically, if you were to rotate a linear polarizer 90 degrees on top of the optical film that sits on top of the display panel, you will never get 100% light blocking. And that is because we do not have a fully linear output from this optical film. We have something that is circular or elliptical in nature. And so it's quite interesting to see that we only have a linear polarizing element on top of this display. And I suspect this is for cost savings measures, but we'll take a look at that in the display module a little bit later. The final element is something we've seen in all of these birdbath modules. It is the field lens element that helps magnify the image from the microdisplay and projects it onto the reflective surfaces that we have in the lens module. So now let's take a look at the lens module and see the structure. Taking a look at the lens module for the Viture birdbath, we actually find something quite interesting compared to some of the other teardowns that we've done so far. Of course, we have the baseline optical module housing that will define the distance between the lens panel and the reflective surfaces. But what Viture has done differently is actually quite ingenious and allows for some cost reduction and process simplification. We still have on the left here the reflective mirror that the light rays will bounce off of, and on the right the reflective polarizer that ultimately is the first path bounce from the OLED microdisplay. But instead of putting a quarter wave plate onto the display module and onto the lens with the reflective polarizer, Viture has actually integrated the quarter wave plate on the half mirror. So we can take a look here. If we put a linear polarizer underneath the half mirror, we see, again, just some fun colors here that are representative of the light that's passing through the beam splitter. But if we take another polarizer 90 degrees to this module, you can actually see 90-degree cross polarizers are going to be completely opaque. So we see the black around the perimeter of the lens. Even towards the right side of the lens, we see very low transmission because, again, we have a very low birefringence material as the lens element. And so this, again, is very minimal transmission. But what we see towards the center of the lens, where the seam of the film removal has stopped, is that we get a nice rainbow effect. And what this is indicative of is that we have a quarter wave plate that has been directly laminated to the half mirror lens. This essentially allows Viture to remove a single quarter wave plate from the manufacturing process. Instead of having a quarter wave plate on the display and then one onto the reflective polarizer, they can put it on the half mirror, and as the light bounces through the quarter wave plate and into the half mirror, bouncing back towards the user's eye will actually change the circularity of the polarization on this surface. So quite an ingenious move, and I suspect very important for cost reduction of these modules, something that I'm sure we'll see in more modules to come that take advantage of birdbath optics. So here we have the full optical module disassembled for the Viture Pro. Again, the display module is on the left, starting with the heatsink, display panel, the linear polarizer, and field lens. And on the right, we have the lens module with the housing of the optical assembly, followed by the half mirror on the left of that housing and the reflective polarizer on the right. What's very unique about the overall system here is that Viture has found a way to simplify the manufacturing and reduce the number of materials needed by putting the quarter wave plate on this lens. This essentially allows the removal of one quarter wave plate from the entire optical system, and now reduces the overall lamination complexity that we have to make this. Now, we do have to put a film that is typically flat and manufactured onto this curved surface, so there will be new challenges for Viture's approach compared to their competitors, but with a similar manufacturing process flow and cost of all of those tools, this design will actually reduce the overall cost of the optical module. So it's quite nice to see some innovation in this space. The final optical component that we'll take a look at is the Electrochromic Module. Again, we talked about how this is essentially similar to a liquid crystal display, but instead of millions of pixels, we only have one large pixel. So we've gone ahead and removed the left side module to be able to take a look at just the module itself. Okay, so here we have one of the electrochromic modules, specifically the left eye module. And so it's helpful to go through exactly how this works. Essentially what we have built in here are two cross polarizers, like the ones that we see here today, which normally would let in 0% of the light. But what we can do in Electrochromic Module is we have a liquid crystal layer. To mimic that liquid crystal layer, I'm going to use this circular polarizer here. And under an applied voltage, we can change that liquid crystal layer so that it goes from transmitting light, or essentially making light at the same polarization as the top polarizer as it passes through the liquid crystal layer, or we can make it completely block the light by changing the liquid crystal orientation so that light coming out is coming out 90 degrees oriented relative to the axis of the top polarizer, which in this case you can see is now fully blocking the light. So essentially that's what we have with our electrochromic module as well. Unfortunately, when it's not powered, we won't be able to see that kind of functionality because we won't be able to switch the liquid crystal on and off. So this electrochromic module is a way that we could use the same concept of liquid crystal light transmission as one large pixel to turn off the light that's coming in from the outside world. It's a really neat module, and it really helps increase the contrast that we have in the overall product when we have the display turned on. We've reassembled the Viture Pro mostly so that we can get power back to the right optical module and test independently the liquid crystal electrochromic cell that we have for the left optical module. So plugging in our pogo pin connector, we can see that we get power on, and we see our right optical module functioning just fine. And if we go to the left stem and push on the electrochromic switch, we can get good functionality to the dimming function. And that does it for the Viture Pro Glasses Teardown. Again, we saw a really unique set of glasses compared to the Ray Neo and X-Reals, primarily in the form factor that allows for the myopia adjustment directly built into the optical module, and the fact that these glasses also have electrochromic dimming on by default, compared to some of the more budget models that do not include it these days. They have static low transmission lenses on the outside. I think the only weakness personally is the pogo pin connector that is a proprietary connector and doesn't allow for USB-C connections that you might have from other headsets or from just other existing cabling. But overall, Viture has really given a great intro headset to the AR markets in their pros, especially devices that can be bought for very similar price points to the Air versions from other competitors right now. And it stands to be seen if they can improve on this with their Luma series. So that does it for this teardown. If you've got any other recommendations for what we should take a look at next, let me know.